So first, a little bit about me. My name's Jimmy Adcock. I am the product manager for the ABEM range of instruments at Guideline Geo, and we'll talk a little bit more about who Guideline are in a minute. I have a background in geophysics. I trained in geophysics at university. I then worked for 13 years as a surveyor in a geophysics company in the UK. I then joined Guideline about 5.5 years ago as an applications engineer, so doing technical support and training for our customers. And just this year, I've taken over the product management role. I'm actually joined today by my colleague, Mustafa, who is our area sales manager for Middle East and Africa. He's based out of our office in Muscat in Oman, and he is your best point of contact if you're in that region for any inquiries about anything you see today in terms of sales or the capabilities of the instrument. But of course, you can always contact me as well. So hopefully Mustafa can say hello in the chat and supply you with his email address there as well, so that you can copy it out of there. So what are we doing here today? Well, this is a slightly unusual one. If you've been in any of our other webinars, this one's going to be a little bit different. So the Zimbabwe Institute of Geomatics asked us if we could run a workshop on how our instrumentation is used for mapping the subsurface. The kind of topic is very wide-ranging. I mean, there'd be a lot of people who are interested in this, and especially at the moment with the pandemic that's currently active, people can't travel as much to get to events. And so the Institute were very kind and said that they were happy for us to actually open this event up to all comers. So our marketing team put the link out on LinkedIn. We put it on Facebook as well, and just said, you know, if anyone else is interested in this, do come along. The reason why it's going to be slightly different is this is going to be quite a bit longer than one of our normal webinars. So this session is probably going to be about 3 hours. You may not be prepared for that, but don't worry, with the platform that we use, this Webinar Jam platform, records the session, and you should be able to use that login that you've got to come back. Log in again, you'll be able to see a replay of the event. So what are we going to do today? Well, I'm going to split it into 4 groups. We'll do 2, then we'll have a decent break, a reasonably long break, and then we'll do another 2 sessions. First session is going to be about the resistivity method and the instrumentation that we manufacture for doing that. Then we're going to move on to seismics. Then we're going to have our quick break. We're going to talk about time domain electromagnetics. And then we're going to move on to GPR at the end. And all the way through, we're going to split it up so that we have an opportunity for me to answer your questions as we go along. So, as I say, just keep putting questions into the chat box, and I'll try and keep up with those as we go through. Little bit of background about Guideline Geo for those who don't know who we are. Those who've sat in these webinars before, I apologize, you'll have seen these slides quite often. We manufacture geophysical equipment via 2 brands. We have the MALÅ brand, which is ground penetrating radar, and we have the ABEM brand, which is Seismics, Transient Electromagnetics, and Resistivity. And within those groups, we have quite a few different product lines. We're spread across the world pretty well. We've got a number of offices that are shown on this map here. So we cover most time zones quite well. As I said, Mustafa, who's in the chat room, he's based in Muscat. I'm actually based in Manchester in the UK, but our head office is in Stockholm. Our R&D, our research and development office is in a town called Umeå in northern Sweden. And our factory is in MALÅ, which is another town in northern Sweden. That's where we manufacture all of our equipment. So these offices that we have spread around the world, they're a mixture of sort of sales and technical staff. But it should mean that you'll have someone in a relatively close time zone to you wherever you're based. We have quite a long history, in fact. We go back to 1923. That was when ABEM was established. ABEM is actually an acronym. It's a Swedish term that means Electrical Exploration Company. So it was set up to find minerals. That's what it was done. Develop instrumentation that could map where minerals were beneath the surface. So that's the ABEM company. And then the MALÅ company grew out of a Swedish geological survey office that was in the town of MALÅ, established there in 1937. So we've been around a while, and this timeline just shows some of our bigger achievements during that period. The big date would have been around 2013 when ABEM and MALÅ, which were at that time separate companies, came together under the Guideline Geo name. And we're very much looking forward to being able to celebrate our 100th anniversary in a little over 2 years' time. Geophysics, why do we want it? Well, basically we want it because it gives us a very complete picture of the subsurface. Traditional methods to investigate sites tend to be invasive, and that might be drilling or digging. But the problem with those is that although they give us, very definite answers, very clear answers, they only give us answers in a very limited place. And so if we drill somewhere, we can't be sure what is happening just 10, 20, 30 meters away, let alone 100 or 1,000 meters away. This is an image that I found on LinkedIn a few years ago, and ever since I've been trying to find whose photo it is because I'd really love to credit them. I've done lots of Google searches and I can't find out who originated this picture. So I apologize to them that I can't give you their name, but it's a really fantastic example of why sort of pinpoint invasive tests can be problematic. So if you were to base your entire interpretation on this borehole and maybe another one that was 100 meters further away, you would have a very different impression of what the geology was compared to the reality. All I do know is that this is in Australia, where you have these very dramatically weathered limestones that are then infilled with sand. So, I mean, this is a very dramatic version, but it serves the purpose. And geophysics allows us to kind of fill the gaps between those invasive tests that we make so that we can have a more complete picture. So let's move on to the more interesting stuff. Let's move on to the instrumentation and what it can do for us. And we're going to start with the ABEM products. And that means it's primarily our Terameter LS2, which is a resistivity instrument, our Walk TEM, which is the time domain electromagnetic system, transient electromagnetic system, and our Teralock Pro 2, which is our seismic system. And we're going to start by looking at Terameter. So I'm going to follow the same kind of pattern with each of the products. I'm going to do some slides on the method, on the theory behind the geophysics that they use, and then we'll look at the instrument itself and its capabilities, and then some case studies. So with the LS2, as I say, that's the resistivity instrument. We're going to want to measure the resistivity of the materials beneath our feet to give us an idea of the structure and the content of the subsurface. So what do we need to be able to do this? Well, the instrument's going to calculate a resistance. That's primarily what it's doing. It's like a very, very complex, just sort of laboratory test system that you might use to measure the resistance of an electrical component. So what we need is we need 2 electrodes in the ground to set up a current flow, and then we need another 2 electrodes that would allow us to measure the voltage at different locations in the ground. And anyone who remembers their school physics classes might be aware of a thing called Ohm's law, and Ohm's law relates voltage and current to the resistance of the material that they are flowing through. So you take the current that's flowing through the circuit, you take the voltage that has been measured, you divide the voltage by the current, and that gives you a resistance. We can, from a resistance, go to an apparent resistivity, and that is our raw data that we will then work from to build up a model of the subsurface. Now, fortunately, all of this in this day and age is done inside the instrument for us, so we don't have to do too many calculations ourselves. And there are two ways, really, two main ways that we would go about measuring the resistivity beneath us. The simplest way that's been around for a very long time and used an awful lot in, for example, water prospection, is a VES survey. So that's a vertical electrical sounding. And this is where we want to understand how the resistivity changes from the surface to a given depth in one location. So we take our 4 electrodes, we inject the current between A and B, and we measure the voltage between M and N. Now, I haven't used these letters. Those are the letters that you'll see in any textbook that you open. It seems to be a bit lost in the history of geophysics as to why exactly these letters are used, but you'll see them in most of the books. So A and B, current in, M and N, measuring the voltage. And for a particular arrangement, a particular layout of electrodes, we will have what's called a focus point. And that's that red cross on the diagram. And the focus point is where those 4 electrodes are most sensitive to changes in resistivity. So the current is flowing through pretty much all of the ground, but this bit of the ground is having the largest contribution to the signal that we record with the voltage electrodes. And if we are to spread the current electrodes further and further out, then what happens is the current starts to go deeper into the ground and our focus point gets deeper. So by continually moving those current electrodes further and further apart, we can gradually sample a deeper and deeper part of the ground. So what do we end up with on the instrument? Well, on the instrument, we have what's called an apparent resistivity curve. So it's depth down one side and apparent resistivity along the bottom. Now, the reason we call it apparent resistivity is because we're taking our measurements from the surface. And because we're taking our measurement from the surface, we can't isolate like one particular point in the ground. As I say, the current is flowing through all of it. So it means that we have this kind of combined effect of everything between the electrodes. So what we need to do is we need to run a process called inversion, and inversion allows us to then come up with a model of the subsurface that represents the true resistivity of the different layers. So it would be something that looks like this. So you can see we've got an apparent resistivity of probably 110 ohm meters, then dropping down to maybe 70 or 60, and then rising up again to somewhere around 300 or 400. So that's basically how it's going to work. Now, I'm talking about the terameter LS here, which is a little bit unfair on one of our other products, which is the SAS 1000. This is an instrument that we've been making for a very long time. It's a very robust and reliable tool for VES, and there may well be a few people in the audience who have used the SAS 1000, and that's still our kind of go-to instrument for VES. It's very well suited to those measurements, very small and light, very capable tool. So what is inversion? We talked about this process of having to go from our apparent resistivity to a model of what we hope is the true resistivity beneath the ground. Well, it works like this. We have a piece of software, an inversion package, and we put the raw data into that inversion package. So we have our apparent resistivity curve, apparent resistivity against depth. What the software will do is it will build a model of what it thinks the ground looks like. And normally it will start with a pretty simple model. And it will then recreate the measurement that we did in the field. It will look at all the settings that we used, and it will run the same survey over this model. It then looks at what data would have come back if the ground really looked like that. And it will compare the two curves. And you can see that, first of all, the curves don't fit. So what the software does is it changes the model and tries again, then repeats our survey, And now adding some extra layers, changing the resistivity of the different layers, it can get a curve that is probably a bit closer to reality. And so the software will keep on doing this. It will keep changing the model, changing the resistivity values, changing the number and thickness of the layers until it finds a model that matches the data that we have brought back from the field, and it will present that model to us as the final result. Alongside that, it will give us a residual, and the residual tells us how reliable that model would be. It tells us how closely the modeled data, the curve from this model, fits the curve from the real world. And so if they're very close, the residual will be very small, and theoretically the model is better. And if they're a long way apart, then the percentage will be quite high. So in theory, we're looking for a lower number to give us more confidence. But the thing we have to bear in mind is the lower numbers are only good if the model is geologically realistic. So the inversion software doesn't know where we were working, and so it could just keep changing the model to get a really good fit, but it isn't geologically realistic. So that's a very simplistic method. It only uses 4 electrodes. If we want a more complete picture of the subsurface, then we can do imaging, or ERT, so electrical resistivity tomography. And in this setup, what we do is we take our 4 electrodes and we move them along a very long cable with lots of electrodes attached to it. And so the instrument switches between different combinations of electrodes, which then moves our focus point through the subsurface for us. So we don't have to do any of the kind of physical switching. That's all done within the instrument. And now what we get is a 2-dimensional picture of the subsurface. And so here we have depth down the side, profile distance along the bottom, and then the apparent resistivity is given to us by the colors. But we do the same thing. We put that into an inversion package so that we can switch between the apparent resistivity values and what we hope are true resistivity values for the subsurface in that area. Once we have that model, whether it's come from the VES type measurement or an ERT measurement, then we can start to make our interpretation. And so different geological materials will have different resistivities associated with them. And the same type of geological material will have varying resistivity based on water content, inherent strength of say, for example, a bedrock unit, whether there's contaminants in it, that will change the resistivity. So we can use that to form an interpretation. Slight problem with it is that, as you can see from this table that shows the range of resistivity values from left to right, and then the rectangles show us the range of values for individual materials, you get quite a lot of overlap in the kind of range of values. So for example, here you can see that clay overlaps shale, it overlaps coal, it overlaps fresh water. So freshwater, shale and clay can be very difficult to differentiate between those. Something like salt water, much easier to spot because it sits on its own, being very, very low resistivity indeed. We're not limited to just looking at how the resistivity of the ground varies across a site. We can also look, by using induced polarization, we can actually look at what we call the chargeability. So this is treating the ground like a battery. So we switch that current on to take a measurement, and the voltage that we want to measure doesn't appear instantaneously. It builds up to kind of a stable level. And when we switch the current off at the end of the measurement, that voltage again doesn't disappear instantly. It will gradually drop away. So what we can do is we can look at how quickly the ground charges up, and we can look at how quickly it discharges, and that can tell us something about the structure and the materials that might be on the site. Now, I've just realized that my webcam preview is over part of the slide. So I'm going to turn my webcam off now, so you don't have to look at my face and we can see a bit more of the screen. Okay, so This is how induced polarization will work. You can see on the screen, we switch our current on. We then leave the current switched on for a short period while we wait for the voltage in the ground that's shown in green to stabilize. Once that voltage is stabilized, then we'll measure our resistivity. And so if we were just doing a resistivity measurement, we would switch the current on in one direction, we would do this wait, measure, and then we would switch the current to the opposite direction, so it flows back the other way, and we would repeat the process. And we do this sort of forward and backward process so that we don't put any bias into our measurement. We don't charge the ground up just in one direction, because that would mean that we would end up having a biased measurement and a measurement that doesn't represent the true subsurface. So if it was just resistivity, it would be current on, positive, measure the resistivity, current on, negative, measure the resistivity again, take an average. Then you would move to your next location. But for chargeability, using induced polarization, we put the current on, take our resistivity measurement, we then switch the current off for the same amount of time that the current was on for, and we map how the voltage disappears during that off period, during that time when there's no current flowing into the ground. Then, same with the resistivity, we put the current on in the opposite direction so we can test it back the other way. Switch the current on, take our resistivity measurement, switch the current off, and then take our IP measurement. And then at the end, we'll take a background measurement just to make sure that there's no drift between measurements. So make sure that we aren't charging the ground up in one direction or the other, and if we are, that we can correct for it. So it's these curves, these drop-offs that we're interested in when we talk about chargeability. Now, a problem with chargeability is that the values we're trying to measure are incredibly small. Like the voltage, when we take a resistivity measurement, will be quite small anyway. But as soon as we switch the current off, it's just going to get smaller and smaller and smaller over time. And when we're trying to measure this voltage that's in the ground, it's always at risk of being drowned out by background noise. So there's a lot of electrical noise in the ground that comes from induced voltages from electromagnetic signals, so like radio, television, mobile phone signals. There is noise that comes from electricity transmission in the national grid. There's noise that comes from industry, all sorts. And what we need to be able to do is to differentiate, to be able to see our IP signal above this random background noise. So what we do with IP is we actually measure over what we call a time window. So we don't just take an instantaneous measurement of the voltage at 1, 2, 3, 4, 5, 6, 7, 8 different locations on that curve. We actually integrate, we're basically averaging over time what the voltage is. And as the signal gets smaller and closer to that background noise, we have to measure for longer to be able to successfully pick out the IP signal from the noise. So our time windows get gradually longer and longer and longer. Why would we be interested in IP? Well, for a start, there are certain mineral types that have a very strong chargeability associated with them. These minerals act like a big battery. They hold on to the voltage that we've generated in the ground and let it go very, very slowly. So those are things like sulfide ore bodies. So these are very, very obvious in an IP survey. The other thing is that just for general prospection, if we look at our table of resistivities that we looked at before, so we've got resistivity from left to right increasing, and then all the different geological materials with all of their overlap. If we then add in the chargeability that we get from the IP survey, which of course we're doing at the same time as resistivity, we don't have to run the measurement twice, we can see that the materials have different values, and that therefore allows us to start to separate them out. And one of the big ones is the fact that clay and fresh water that have very similar resistivity values have quite different chargeabilities associated with them. So it can be really useful there. So what are the applications of chargeability? Well, hydrogeology, hydrogeophysics, looking at the difference between clay and groundwater, trying to differentiate where you might have saline intrusion, looking at organic soils such as peat, and also getting an impression of permeability. So this is how well water can transport through a rock unit. So this is quite important. If you've found an aquifer, how do you know whether or not, when you sink a well at one side of that aquifer, how well is it going to be able to draw water through that rock unit? And research has been done with IP to try and determine something about the connectivity of the spaces that contain the water. As I said, mineral prospection, that's historically, that's been the kind of big use of IP. And now increasingly, it's being used for study of pollutants. One thing is to map landfill sites, so big buried refuse pits. We used to bury rubbish on the outskirts of towns and cities, and now the towns and cities are getting bigger, and we need to build over the top of these refuse pits. And the very old ones tend not to have very good records about how big they are, so it's important to understand their scale. And then also contamination plumes, so material that is leaking out of industrial sites, from saline waste from reverse osmosis plants, perhaps, or the chemicals that leak from landfill. So there are a huge number of applications for resistivity. And why would you want to choose the terameter? Why would you choose the LS2 for doing this particular type of survey? Well, one of the great things about it is that it's the versatility of the system. We have this massive range of applications that we can use it for, and we're not limited to just a single line of electrodes. We can actually do 3D survey as well, where we would have a grid of electrodes laid out and then be able to generate a 3D volume of data. Unfortunately, to do that, you kind of need a lot of electrodes. So although the LS2 itself has inbuilt switching, so it can we can address up to 81 electrodes in a straight line, or 64 in a 3D layout, just with the instrument on its own. If we want to have a bigger spread of electrodes, we can actually just bolt on external switch boxes. And every time we add an external switch box, we add another 64 electrodes. And we can have a lot of these. So we can actually go up to 16,384 electrodes if it's absolutely necessary. I don't think anyone would have the patience to do that, but at least we know it's possible. We can use non-polarizing electrodes. So these are very useful for very detailed IP work, or a method called SP, which is self-potential or spontaneous potential. This is where we never inject current in the ground. We just measure natural voltages. And you find that large mineral bodies will have these natural voltage associated with them. And we can find those using these non-polarizing, non-metallic electrodes. We're not limited to survey on land or at the surface. We can use a borehole logger. So we literally just take absolute resistivity measurements in water-filled boreholes down to depth. And that allows us to have a very detailed impression of how the resistivity of the various geological units change. We can even put imaging cables with lots of takeouts on them down boreholes, and actually do imaging from within the borehole, so that we get like a 2D profile, like a vertical 2D profile from the side of the borehole outwards. We can do marine survey, so we can have fully waterproof cables. So this is a marine data set that we'll look at in a bit more detail in a minute. And we can have completely custom connections. So like these boxes where we connect those to the inputs on the instrument, and then we can just connect anything directly to the switch unit inside. And that can be useful for doing like laboratory measurements, or I heard of a customer who was mapping where there was dead wood inside trees, and they had like a series of pins pushed into the trunk of the tree, and then the pin was just connected back via a small lead into one of these connection boxes, one for each of these little pins, and they could measure the resistivity of the tree trunk. So there's very little that we can't do with the instrument. It actually has a hardware licensing scheme system. So what that means is that every instrument has all of the hardware in the box. We have a range of different models, and when you choose the model that you want, the instrument will be set up for that particular specification. So we have very low cost instruments which have a limited number of electrodes and limited output power and limited sort of accuracy on the measurement circuits. And so you can sort of get onto the ladder of resistivity equipment at quite a low level. And then if your requirements change over time, you need more electrodes, or you want to have more power, or you want some of the more advanced features, then you can pay for an upgrade. You don't have to send the instrument back to Sweden to have it upgraded. We will just send you a new license code. You enter that onto the instrument, and the new specifications will then be available to you. If you're interested in chargeability, doing induced polarization, then the LS2 is unique in that it offers what we call 100% duty cycle IP measurements. So if you remember back to our example of what the current injection looks like when we take an IP measurement, we said that we switch the current on, then we switch the current off to take our chargeability, to see how the voltage varies when that current disappears. Then we put the current on in the opposite direction, and then we switch the current off again. And that is one measurement. And we might have to repeat that measurement. We might have to stack it to get a good quality reading. So we're talking about quite a long time to take a single data point. With the 100% duty cycle, what we've done is we've taken the kind of traditional resistivity method of switch the current on, then instantly change the polarity, and then switch the current back and just keep switching it positive to negative, positive to negative. And what we do is we actually extract the IP effect. We extract the change in voltage from the point where we change the voltage from positive to negative or from negative to positive. Because the reason that we have this delay before we start measuring resistivity is that we're waiting for the voltage in the ground to stabilize. And why do we need to wait for the voltage to stabilize? It's because of the IP effect. So by doing this, we can actually take out the switch off time. So we make measurements quicker. So if we don't mind about how much time we spend in the field, we can actually just take more measurements. We can repeat measurements, and we can improve the quality of the data that we take home. Or we can get our result quicker because the individual cycles are shorter. But also, we're now not measuring just from a positive voltage down to zero and then from a negative voltage down to zero. We're actually looking at the shape of the curve from positive through zero all the way through to negative. So we have a bigger effect that we can look at. And when we're talking about these small voltages, that is much, much better in terms of being able to build an accurate model of the chargeability. So effectively, as it says down here at the bottom, it's faster, we've got bigger responses, therefore we should be able to come out of this procedure with better data quality. The LS instruments have the ability to connect remotely. So if you're connecting via the Wi-Fi, then you can basically control the instrument on any device. So this is on a laptop, this is on a mobile phone. So you can just control the user interface from there very, very simply. We can also then connect the instrument to the internet. So we can either connect via a hardwired system through an Ethernet port, or we can put a 3G adapter onto it so that we can connect via the mobile network. And that allows us to take measurements without even being close to the instrument. We can leave the instrument on site, and that gives us opportunities to do things like monitoring, where we take data at a series of different times. So here's a case study that's just looking at like a monitoring project, and this is a 3D data set. So you can see rather than just a 2D profile, we've actually got a cube of resistivity values. And we're not looking here at absolute resistivity. Here we're looking at change in resistivity. So if you see blue colors, that means that resistivity changed down from the starting value. And if you see red, the resistivity has increased from the starting value. And what we're looking at is how the resistivity over a landfill site changes after a rainfall event. And so these are resistivity measurements that have been taken over a number of days. And as it comes back to the start, I'll talk you through it. So we have the rain on the first day, changes the resistivity near surface. Resistivity drops because there's more water in there. As that water gets into the pit, it causes chemical reactions. Those chemical reactions release gases, and the gas is non-conductive, so it raises the resistivity. So it drops initially as the water lands on the site. Chemical reaction causes resistivity to increase. So let's take a look at some other case studies just very quickly. This first one is a road improvement scheme. So this was in Sweden, between two places that I wouldn't want to try and pronounce because I know that there's more than one person who can speak Swedish watching at the moment. So this was a kind of regular highway with one lane in each direction. And they wanted to upgrade 16 kilometers of that road to being 2 lanes in each direction. And that meant that there would be an increase in traffic and potentially then an increase in pollution into the surrounding soils, because there would be more oil, fuel, salt that gets spread on the road in the winter. All of that would be washing off the road into the soils. And in this region, the local municipalities all take their water from the ground. So they did 4.5 kilometers of the 16 kilometers with traditional geotechnical investigations to work out whether or not the groundwater might be at risk, because they know here that there is a big, thick layer of clay, and the clay seals the groundwater so that any pollutants aren't going to actually be able to get into it. But if that clay is missing, then they're going to have to put some kind of remediation in to catch the potential pollutants. So they did 4.5 kilometers the hard way, and then they did 11 and a bit kilometers using resistivity. And what they did was they did very, very long profiles. So you can see down here, these are kilometers. So each one of these numbers is showing a move of 500 meters at a time. And they've basically simplified the data set to make it more manageable. So you've got quite big cell sizes in here. But it was quite an easy task for them with the resistivity. Due to the fact that it was quite clear boundaries between the different materials. So you've got at the top, you have a glacial till, and at the bottom you have a bedrock, and it's the bedrock that holds the groundwater. So bedrock at the bottom, glacial till at the top. And then in the middle, the very low resistivity is clay. And so that clay is what's sealing the bedrock, is stopping pollutants getting into the groundwater. And what they were interested in was anywhere where during the last glaciation, the last ice age, where the movement of the ice might have scoured away the clay and left behind it sands and gravels, because the sand and the gravel will have a higher resistivity and it will allow the pollutants to percolate down into the bedrock. So very, very simple for them to make the interpretation. And then once they had made the interpretation, all they needed to do was highlight the regions in blue where some kind of protection material would need to be put in place, or extra drainage to catch the runoff from the road and maintain the integrity of the groundwater supply. And they estimated that if they had to put that that protection in along the entire route of the corridor, it would have cost them $5.5 million. So the cost of the geophysics was nothing like that, nowhere near. So it was very, very worthwhile doing that. I've just seen in the chat, I've had a couple of private messages just to say that a couple of people are unable to join. The link that they've received isn't working. So I'm just going to get them a link. So if you can bear with me for one moment. Let's see if this will work. Let's just copy this link. Okay, I'm going to put a link in the chat. And so if you know anyone who is trying to connect to the meeting and can't get in, just try sending them the link that I've just put into the chat. It's kind of like a back door to the meeting room. So hopefully if they try that, they should be able to get in. And of course, as I said at the start, if not, the whole presentation is being recorded, and so we can we'll be able to share that with them afterwards. So hopefully that will work. Okay, right, back to the presentation. This next one is aquifer prospection. Again, this is in Sweden. You wouldn't guess that that's where our main offices are. So this is a place in kind of sort of mid to north Sweden, where they take all of their drinking water from the ground supply, and the municipalities there were growing at quite a rate, and therefore the existing infrastructure for water was not sufficient. So they needed to find new ones. Now, in this region, it's a very, very hard kind of crystalline type bedrock, not very porous. And so in this region, what you find is it's quite an easy process with resistivity, because in general, the bedrock is very high resistivity. The water is retained or pools in regions where you have fractures in the bedrock. So where you've had tectonic movement or, you know, some kind of shift in the geology, that causes stresses, that causes the rock to fracture, and then groundwater pools in those fracture zones. So all they were looking for were these very distinct areas where the resistivity suddenly dropped, and they could then target those for their drilling. This one's a geotechnical case study. So I've tried to kind of give a spread of different applications, different types of job for the resistivity. So this one is looking at the quality of bedrock ahead of putting in a new subway tunnel. Now, they wanted to extend this subway across between a couple of the islands that form Stockholm, central Stockholm in Sweden. And the issue that they have is that the geology is very well known on land, but the geology isn't very well known for the bit between the islands in the water. So all they did know was that there is geologic activity that has caused fractures and weak zones, and that they would have to cross those. So because this was going between the islands, this had to be a marine survey, and that meant that they were using slightly different cables. So we have different cables depending upon how you want to use the resistivity measurement in water. So if it's deepish water that's going to be for quite a while, like up to 40 meters, then we have dual purpose cables that can be used on land, or they can be used in the water, or as in this case, marine cables that are much bigger, much heavier. They have a big strengthening member through the middle, so that if they get caught on anything on the riverbed or the lake bed, that they're not going to break, and have much better waterproofing. They have solid stainless takeouts that allow the current to flow out of the takeout and into the water. So we don't use electrodes as such, we just let the current flow out. And we can actually use exactly the same protocols that we would use on land. So although we changed the hardware setup slightly, the actual method of collection is very, very similar. There are two options. The simplest in terms of deployment and data processing is to have your cable floated at the surface, because then when you come to do your processing, this is really no different from a land survey. It's just that that top layer is very uniform resistivity, and the modeling software will just see the water as another layer. But the downside of this is that you lose a lot of penetration. You don't have very good image of anything at depth beneath the water, because you lose so much energy into the water itself. The current dissipates very quickly. So to get around that, then the alternative is to lay the cable on the bed of either the river or the lake. And this is great because you get much better penetration, but the downside is it's more complex, because we need to know, first of all, the topography of the bed, because the electrode takeouts are no longer in a nice flat line. They're probably going to be going up and down a bit. We also need to know the resistivity of the water itself and how deep the water is, because processing software, inversion software, always assumes that you're working in what we call a half space. That is, you have air above the takeouts, and therefore the current can only go in one direction. It can go in the ground beneath, so it can go in that half horizon. It can't go upwards. But as soon as you put the cable on the bed of a river or a lake, then the current can go in both directions, and we need to be able to account for that. So this is the data from 2 lines on that survey, and what we've got is where the cables would have been laid along the bed of the water, and the bed is represented by this interface here. So the white bit is effectively the water, and then we've got the geological materials beneath. And the interpretation, again, is based on the resistivity, whereby bedrock, which is competent and solid, should have higher resistivities. Bedrock, which is fractured and therefore allows water to seep into it, will have a lower resistivity. So they categorized it as the sediments, questionable quality bedrock, improving quality, and then good quality bedrock being the very highest resistivity. And that allows the engineers to plan better for what they're going to have to do when they come to actually tunnel. And this was a pilot study, so they did a bit of invasive testing as well. So these black dots are where they used a CPT, a cone penetrometer, to push through the sediments until they hit solid bedrock. And you can see that there's a pretty good correlation between those CPT strikes on bedrock and the increase in resistivity. So let's have a look at 2 IP examples now. So the first one is one of these where we talked about mapping landfill sites, and this is from South Africa, where they were found that drinking water was gradually seeing higher and higher levels of contamination within it. And the suspicion was that it was coming from some kind of landfill site where chemicals were leaching out of the landfill and getting into the local aquifer, which was stored in the bedrock. So they undertook IP and resistivity, as I say, measure them both at the same time. The IP survey was excellent for defining the limits of the pit. So you can see here this red, very high chargeability. That is the waste pit. That is the big hole in the ground that's been filled with rubbish. And because you've got mixture of plastics, metals, alkalis, acids, salts, minerals, it acts like a massive battery. It holds onto that voltage for a very long time. And it's very clearly different from the natural materials outside of the pit. So they knew exactly where the extent of the waste was. So they knew where they would have to dig down, potentially, to get to that waste material, but they couldn't see where it was getting into the bedrock. However, the resistivity data allowed them to see the difference between the overburden and the bedrock being much higher resistivity, and they could see that the chemicals that were leaching out of the pit were getting in via some kind of fault in the bedrock and therefore getting into the water supply. So the two between them were useful because the resistivity showed them what needed to be protected. It's this fault region that needed the protection, and the IP showed them how far the pit extended towards that fault. And then the final one for the resistivity is gold prospection, because whenever I'm out doing survey, people always ask me if I've ever found any gold. So this is customer in Asia, and they're doing the kind of pre-investigation before they move in for drilling. So they've done some airborne results, they've done some airborne survey, and then they had gone in with resistivity to get some greater detail. And they're using IP. It's shown to be very good for detecting these mineral veins that can hold the gold. And the reason why IP is important for this is detecting that mineralization is that if you look at the resistivity alone in this region, the bedrock has very high resistivity. And we can see that there are regions where the resistivity drops off that could be associated with that mineralization. But equally, it could be just fractures in bedrock that are holding water. So we need more information. And so by then looking at the IP data as well, then we can see where we have these spikes in chargeability, and we would expect those spikes to be associated with the mineralized veins. So they took a series of profiles that allowed them to see the strike of these mineral veins, and then also identify where the vein comes closest to the surface, so that the test drilling would be as simple as possible. You don't have to go as deep to actually get a sample out and analyze it. Okay, so that is the brief run through of resistivity. I've also just had a quick question in on the chat, to just asking if we're going to do all of the methods: resistivity, seismic, GPR, and TEM. So, yep, anyone who's joined us recently, that is what we're going to do. We're going to start. We've done resistivity. We're going to do seismic next. Then we're going to have a break. And then we're going to do TEM and GPR afterwards. So I'm just going to see if there are any other questions that I've missed whilst talking. No, you all look very friendly, though. You've all been saying hello, which is excellent. Great. Okay. Then in that case, I'm going to move on to the seismic, the Terralock Pro. That's our seismic instrument. And we'll follow the same pattern here. What we'll do is we will look at the theory, first of all, and then we'll look at the instrument and a couple of case studies. So, seismic. There are 3 types of seismic wave, and we can use all of them to tell us something about the subsurface. The first type of seismic wave in any seismic event is called a P wave. P stands for primary or pressure. So primary, it's because if something shakes the ground, these are the fastest waves. They're the ones that arrive at your sensors first. And the reason they move fastest is, as this little diagram is trying to show, is that the particles that are transferring that energy are vibrating in the same direction that the wave, the seismic wave, is moving through the ground. So they're moving everything really quickly. And it's really good. These are compressional waves. So they're squeezing the ground, and they give us a really good indication of how strong a bedrock might be, or how strong a material is. So we can use those for refraction surveys, allowing us to look at like depth to bedrock or bedrock quality. The next type of wave that would come through in a seismic event is an S wave, and S stands for secondary because they're the second to arrive at our sensors, and they're also known as shear waves. Now these travel obviously a bit slower because they're coming in second. And the reason for that is that now the particles are moving at right angles to the wave, the seismic wave. So you can see the particles move up and down, but they're also moving left and right. So we've got shear action in sort of two directions. Now, these are great because these tell us something about the stability of the ground. So kind of shear strength tells us how they would withstand loading from one side. And then the final type of wave, very slow, very large. These are surface waves, and these move a bit like waves in the ocean. So you can see here, this is one type of surface wave called a Raleigh wave, and the particles kind of roll as the seismic wave moves through. And again, these are very good at telling us something about the stiffness of the ground, about how well it will withstand a shaking event, for example, like an earthquake. So, as I say, these aren't happening in isolation. They're all kind of happening together. So if we have a seismic event, whether that's me hitting the ground with a hammer or an earthquake, if you've ever been unfortunate enough to be in an earthquake, the P wave is what happens first. And you don't feel the P wave normally, you hear the P wave. It doesn't shake the ground a lot, you just hear this kind of very low rumble. Then the ground starts to move, and that's the S wave coming in. And then the damage starts to happen. Then the big motion comes through, and that's the surface waves at the end. So they're all coming through one after the other. And of course, then in the ground, they're all happening at the same time as well. So we've got these reflected waves. We have these primary waves, shear waves, and surface waves. And then when they're moving through the ground, then they're being affected by the structure. So let's have a look at what happens as that wave moves through the ground. So we have our seismic event, and let's say, for example, this is me hitting the ground with a hammer. So the first thing we have is direct waves. So these are waves that have not been affected by anything. They're moving through a layer that is homogeneous, i.e. it doesn't change, it's the same velocity throughout. And they just travel then. They travel out, they spread out in a straight line in all directions. When they reach a layer boundary, an interface, a different material, then we're going to have some form of interaction. And that interaction is based on the velocity, which is related to primarily the density of that material, the rigidity of that material. So if the velocity contrast between the two layers is very big, then you get a bigger effect. So here we can see some of the energy gets reflected back to the surface. And if this velocity in this layer is much, much bigger, or greatly different from the velocity of the material in this layer, then we will get more energy reflected. If they're fairly similar, then we get less energy reflected. Some of the energy will travel into that second layer. Now, if the energy is coming straight on towards the layer, then it will continue in the same direction without being deflected in one direction or the other. If, however, it's a wavefront that meets this boundary at an angle, then we have refraction. So refraction is where the wavefront gets bent and it gets sent in a slightly different direction through the next layer. And again, the amount that it bends is related to the change in velocity. So if we have a big change in velocity, then we have a big offset between the directions. And if we have a small change in velocity, we get a very small offset. So if seismics is new to you, this whole concept of refraction can be a bit confusing. And one of the things that I tried to sorry, press the wrong button. One of the things that I tried to use to explain this is the concept of a car driving through the layers. So I'm going to attempt to draw a very bad image of a vehicle. So this is a car looking from the top down. Okay, so I'm just going to draw it as a rectangle because I'm not particularly artistic. And our car is a fairly regular vehicle with 4 wheels, 1 on each corner. And so if you imagine that the car is driving through this top layer in this direction, when it's traveling through that layer at the same velocity, then it will travel in a straight line. At this point, however, where the car is traversing from one layer to the next, if you imagine that this layer is much faster, this wheel wants to travel at that new speed, at that faster speed. This wheel, however, is still in the slow material, so it doesn't want to speed up yet. So what happens is this faster wheel gets pulled around this way, like that, gets pulled in this direction until that wheel is also in this layer. Once both of those wheels are in the same layer, they're both traveling at the same speed, and it will continue then on the new in the new direction. So the same thing will happen when it gets to the next layer. When you've got one wheel in the fast material, one wheel in the slow material, it's going to again pull the vehicle around slightly, and then once both wheels are in, it will travel in the same direction. So this is what's happening with the wavefront as well. When it's half in one layer and half in the other, the faster side is going to generally pull that wave to one side, and then once the wave is fully in the layer, it will carry on in the straight direction until it gets to the next interface. So we get to our next layer, and we have a repeat of what happened at the first boundary, which is that, I'll come back to those. We get some reflected data and we get some refracted data. Now, as you can see at both of the layers, as the energy gets further and further out from the center line, the angle gets greater and greater. So you can see that it's gradually getting more and more closer to horizontal. So at some point, there'll be energy that hits the interface and gets bent along that interface, travels horizontally. And those waves that are bent to such a degree that they end up traveling parallel to the surface are called critically refracted waves. And a critically refracted wave is what we're interested in from a refraction survey point of view, because then your wavefront is heading back up to the surface. So all of the time this energy is traveling along here, some proportion of it will be getting back to the surface where we can measure it. And then the same thing happens down here. You'll get some energy that will be critically refracted and allowed then to travel back up to the surface where we can measure it. So we have reflection survey, we have refraction survey, and then we have surface waves that we can use as well. So let's look at those in detail. Let's look at those 3 different types of survey. Refraction is probably one of the most commonly used for kind of site investigation engineering works, because it's a very quick and easy way to get a continuous profile of bedrock depth. It's a very useful way to find out the quality of the bedrock. So faster velocities will tend to suggest more competent, solid bedrock. Slower velocities tend to suggest a looser material or broken bedrock. So with refraction, very good for these fairly basic engineering tasks. And the processing is nice and simple, because all we're interested in is what the energy that arrives first at each of our sensors. So looking at a single shot position during a survey, I'd hit the ground, and here we're working in the center of our spread. And what we're going to look at, as I say, is the first arrival at each geophone. So here are my set of geophones. They're going to measure how much the ground vibrates, and they're going to send the vibration signal back along the cable to our instrument. So I've hit the ground. The first arrival at the two nearest geophones are going to be direct waves. They are waves that have only traveled through that top layer. And so if I know how long it's taken for this arrival, this first geophone to start shaking, if I know how long that's taken, and I know how far those geophones are from my shot position, I can work out the velocity at which the energy moves through this top layer. Because it's a direct line, it's very easy. Distance divided by time, there's my velocity. Then what happens over time is something slightly strange. The energy that travels into the deeper layers, which we usually assume to be faster layers because they're more compact, you're getting into harder bedrock normally. The energy in those is traveling faster. And what happens is that it overtakes the energy from the direct waves because it's traveled through these faster layers. So if you look at what happens as we get further away from the shot position, the first arrivals on these next set of geophones are coming from layer number 2, and the first arrivals on the outer geophones are coming from layer number 3. So again, it can be a bit confusing as to how can that possibly be when these are traveling so much further. So I'll go back to using cars as an example. And as I said right at the start, I'm based in Manchester in the UK. And we have one thing we're famous for, and that is 2 football teams. Manchester City on the eastern side of the city and Manchester United on the western side of the city. Now, if I was to take 2 people and ask them to drive between Manchester United and Manchester City, and take 2 different routes, obviously it's going to take them different amounts of time to get there. If I send one person on the most direct route, so I've asked Google for the shortest distance between the 2 football clubs, it tells me that it's 4.2 miles, 6.8 kilometers, and that in a car, it's going to take me 21 minutes to do that journey. So that's the shortest route. If I then send someone on a slightly longer route, but one which uses the ring road that goes around the city centre, the expressway, then the distance is longer. It's 4.4 miles, it's 7 kilometers, but it's a lot faster. So even though these 2 people have shared the same first part of their journey, i.e. layer 1, they've deviated on the second part of their journey. So layer 1 still, layer 2. Then at the end, they've both used the same roads, but the person who's gone through layer 2, the faster route, has arrived much faster. And that's basically what we're doing. That's what we're saying in refraction survey. We're saying that although the paths are longer, the energy is traveling much faster, and therefore the energy that travels through those deeper layers will arrive sooner at the geophones that are further away from the source. And the further away we put the geophones, the deeper the layers that we're going to be able to sample. So as I say, we're only interested in our first arrival. So this is what we would see on the screen. These are the vibrations measured on each of our little geophones. They're plotted on the screen, one trace for each geophone. And we can see that our shot position is right in the middle here. And then gradually the time taken for the first arrival, so that's that first kick, gets later and later into the trace. So all we have to do is tell the software where that first arrival is, just pick it out. And then once we've picked it out, we can already get an impression of the different velocities. Because if the arrivals are all getting later in a kind of uniform pattern, that suggests that the energy is moving through a single layer. And then if that gradient changes, then we can see that we've got a new layer. And actually, if we measure the slope on this, so we've got distance from the distance between the shot to the geophones, and we've got time down the side, the time it's taken for that first arrival to get there, that slope will give us a velocity. So we can tell the apparent velocity of layer 1, because again, apparent velocity because we're measuring from the surface. Then the slope of this will give us the apparent velocity of layer 2. So we take those values, we put them into inversion software, exactly the same like we did with resistivity, And we ask the software to try and find a model of the subsurface that will produce the same set of first arrivals for a given shot position. And so we take 1, 2, 3, 4, 5, 6, 7 shots normally for a refraction survey, give that information to the software, and it will return me with a model. And you can see here that you've got distance along the profile, depth down the side, and then the velocity is given by the color scale. And as we say, with the resistivity, we can then look up the velocities for different types of geological material. And the range of velocities will then give you an indication of either water content or the structural rigidity of that particular material. Again, like with resistivity, they're not unique. There's big overlaps, and so it's often useful to have some other form of information, and quite often that will be your own knowledge about the geology that you're working over. So you will know what type of geology should be beneath your feet, and therefore you can use that to inform part of the interpretation. We can make kind of generic statements. So typically loose material near surface, you know, the stuff you're stood on, will be values of 600 meters per second or below. And the looser they are, the slower that will be. If you see a sudden increase up to about 1500 meters per second, that typically means that you're still in loose material, but it's waterlogged, so you've hit the water table. And if you're looking for good solid bedrock, then velocities in the thousands of meters per second are what you would hope to see. So next is the reflection survey. So this is using the energy that is reflected rather than refracted. And here we're doing something slightly different. Here we're not primarily interested in velocity to start with. What we want to do is we want to build up a 2D image of the ground, of the true structure. Rather than a velocity model, we want the structure of the ground. The problem with reflection survey is that although it gives us very detailed data sets of the various horizons, it takes a lot more effort than refraction survey. We need to do a lot more shots, many more shots, and the processing is a lot more intense. It's very easy to get the processing wrong on a reflection survey and not get a very good result from it. However, it is incredibly useful for looking at stratigraphy. It's very good for mapping geological features such as faults, looking for where there's an offset between horizons. It's great for looking at like void sinkholes that might be forming at depth where perhaps you can't use GPR. But we can also use it for things like depth to bedrock. But normally you would head out with a refraction first because it's much simpler. So in reflection survey, again, we're hitting the ground, generating a source from something, either a mechanical source or here me sweating slightly with a sledgehammer. And the energy extends out, as we said, through that first layer without deviating until it reaches an interface. And then some proportion of the energy will be reflected back to the surface. And the angle that it gets reflected back at is equal to the angle that it meets that interface. So it comes in and goes back out symmetrically. Again, depending upon the velocity contrast between the layers, some of the energy will go into the next layer, and then we'll get more reflections from subsequent interfaces. So in this very simplistic layout, you've got a single shot, and we're just using 4 of our geophones on our spread. And what we would do is we would then gradually move the shot and the number and the active geophones along the line. And you can see then that we gradually build up a picture of the subsurface. So you can see that this is a very slow process. A data set doesn't look any different from a refracted data set. The individual components are just shot records. So you have a shot location and then your first arrivals and then some reflected features, ground waves, air waves, a whole bunch of stuff in there, but an individual shot record still just looks the same. And what we have to do is we want to try and get to the equivalent of having the shot and the receiver at the same point. Because obviously here, the issue is that if we shoot from here and record over here, we have a large amount of material in between, and we don't know where these layers are to start with. So we don't know what this path length is. We don't know what the angles are. What we want to try and get back to is just being able to recreate what would happen if we had a single shot and a single receiver right next to each other, because that would just give you all of the layers directly beneath that position. So it would go down, some reflected back. It would go down, some reflected back. And you could just take the times that it's taken for that energy to be returned, convert it to a depth, if you have an estimate of the velocity, and everything would be simple. But to do this, one shot, one geophone, to build up a profile that might have to have a few hundred traces in it, or even a few thousand, would take forever, and you'd end up killing your geophones probably. So what we do is we take our series of shots and we reorganize the data, and we reorganize it to pair together geophones and shots that share the same reflection point normally. There are different ways to do it, but that's one of the more common. So you use what's called a common midpoint or a common depth point gather, and what you say is, right, trace number 12 on shot number 1 and trace number 16 on shot number 2 will both have sampled the same point in the ground. Now, the only difference would be that perhaps the shot and the receiver might be further apart, but they are all sampling at the same location. So we take those traces that pair together from all the different shots and we make a new plot called a gather. And so now we have all of these different traces. And basically this first trace will be where the shot and the geophone were almost in this kind of situation, almost directly over the top of the point in the ground that we're interested in. And as you get further to the right, the distance between the shot and the geophone gets greater and greater and greater, but the point that the energy was being reflected from in the ground is still the same. So the reason why all of the layers kind of seem to dip is because of this increase in distance. That means it takes longer for the energy to travel. So we do some velocity analysis on it, and we apply a move out correction. So what we're saying is that if we know what the distance is and we know what velocity it's traveled at, we can correct this offset, and we can then plot all of the traces as if they were the distance traveled was the same. And so you end up with this gather, where now we're seeing the true horizons in the ground. And these are all from the same point. So this is all from one location. So what we then do is we add all of these traces together mathematically, and that's called stacking. So we've stacked all of those together, and that improves our signal to noise ratio. So you might have, especially in the later part, a lot of vibrations from maybe traffic or wind or people walking around, but that will be random noise. And by adding all of these traces together, we can minimize the noise and just keep what the true reflections from actual layers are. And that gives us a single trace. And then we repeat that process over and over again. And that gives us a series of traces that will then allow us to build up a full profile. So you see, compared to refraction processing, there is a lot more work to be done here. But the goal is that we can actually map both stratigraphy and isolated structures far more clearly and far more detail than we would ever be able to do in a refraction survey. And in fact, if we use horizontal geophones, we can run an inversion on the data set, or the equivalent of an inversion on the data set, and generate a velocity model of the shear wave velocity. And that'll help us then not only to see the structure, but to see the stability. Another thing is that obviously I've just seen a question come in on the on the chat, so it's a good point. Obviously, with refraction and reflection, the difference is that we're looking for more detail here. When we set the system up, we are hitting the ground with a hammer, or we're hitting it with some kind of mechanical device, or we're shaking it with a vibration instrument, vibration tool, and that's generating a certain amount of energy, and we want to record those vibrations. And the geophones that detect it, the way that they work is they have a weight on a spring, and they vibrate up and down as the ground moves. And depending upon the design of the springs and the size of the weight, those geophones will be more sensitive to certain frequencies of vibration. And so if we use geophones that have a very high frequency, then that theoretically will allow us to have more detail, because the higher frequency vibrations can refine layers that are closer together, whether it's trying to make a reflection survey or build a refraction model. Whereas the geophones that have a lower frequency, they don't see in such detail, but they do allow you to image deeper. Lower frequencies tend to propagate more completely through the ground. So you would find that the ground absorbs that vibration, and it absorbs the high frequency vibrations quickly and the low frequency vibrations slowly. So if you use a low frequency geophone, you'll be able to see that energy that's hung around for longer, and therefore the energy that's traveled deeper. If you use the higher frequency ones, you can get more detail. So typically you use higher frequency geophones in reflection survey, because normally you'd be looking for finer detail than you would on a refraction survey. Okay, let's look at the final type. So we've looked at refraction and reflection. We're going to look at surface wave survey. And every time I kind of do this section, I always give a little shout to this website called www.masw.com. It's owned by a company called Park Seismic, and they actually make software for processing surface wave data. But their website is fantastic. It's a really good resource for learning about surface waves, and I've learned a lot from that website, and so I feel slightly indebted to them. So I always give them a mention whenever I do this surface wave. And so do check that website out if you want to know more about surface waves, because there's lots of really useful stuff on there. Okay, so with surface wave, what we're doing is we're using those late big vibrations to try and map the shear wave velocity, and we can do that in 1D. So we just get how the shear wave velocity changes with depth underneath a single point. We can build up a 2D profile of shear wave, or we can map in 3 dimensions. Biggest use of surface wave survey is normally earthquake resilience. So predicting how well a particular volume of ground will withstand a shaking event. So you would want to do that before you begin to build. But it's also incredibly useful for soil stability studies, looking at whether soils might be prone to liquefaction. But we can use it for the other kind of typical stuff like depth to bedrock studies as well. But the stability of the ground is where surface wave really comes into its own. So MASW is an example of this, multi-channel analysis of surface waves. And as I say, what we're trying to get to is we're trying to get to a shear wave velocity, because shear wave velocities are very useful in a lot of engineering parameters. If you're measuring stiffness, then one of the things that you put in there is the shear wave velocity. So it's a useful thing to actually quantify the stability of the ground, rather than just like we would with a refraction survey say, well, the velocity here is higher than it is over there, therefore here is stronger than there. With taking these shear wave velocities and putting them into these engineering equations, you actually get a number out for how well that ground will withstand a particular load. And the reason why surface waves are good is that, if you remember, we talked about in the seismic event, P waves being the first arrival and small S waves being the next arrival, slightly bigger, and surface waves being right at the end and really big. Because they're big, they are less affected by ambient noise, so the vibrations that are around us all the time, and therefore it's easier to get a good result, especially in noisy environments such as urban areas. Certainly much easier than it would be to try and extract the S wave velocity directly from, for example, S-wave refraction or S-wave reflection surveys. So here's where it gets a bit complex. It's probably the most complex in terms of the theory behind it, but actually the software that you use is pretty simple. So surface wave methods all rely upon the fact that the ground we have dispersion of the frequencies of vibration within the ground. So the way to think of this is a prism that splits white light into a rainbow. The white light gets shone into one side. The prism splits that light into different frequencies, and so physically separates out the red, the orange, the yellow, the green, the blue. The ground is doing something similar with seismic energy. It's filtering the lower and higher frequencies. And if we understand how it's filtering those frequencies out, then we can start to understand the structure of the ground and the stability of the ground. So what you see here is a seismic event, and this is showing the frequency up the side against time. So it's looking at how the different frequencies move out from the original source, and these dots pick the same point on the wave, on the seismic wave, for the different frequencies. And so you can see that the low velocities are moving slowly and the higher velocities are moving very quickly. So if we can look at the phase velocity, then in that case, we can actually understand the structure. So all we do is we take our survey and put our data into the processing software. But how do we get the data in the first place? How can we get to the point where we can find out what the phase velocity is? Well, there are two options. There's an active method and a passive method. In active survey, it's us who's generating the energy, and the layout looks an awful lot like a kind of typical refraction survey. We'd be using something like either an accelerated weight drop or a hammer. And really, as I say, the only difference between the method for MASW and refraction is actually what we do with the shot records afterwards. For active surface wave, typically you're talking about a maximum depth of 30 meters. Below that, we can't really get enough energy into the ground, low enough frequencies to make the ground move in those big rolling patterns with just a hammer or a weight drop. So typically it's about 30 meters maximum depth, but perfect for kind of engineering work. So then the other option is to use the passive method. And this is different. Here we would use very low frequency motion that is coming from all sorts of different sources. So locally, it might be traffic and construction work, trains. Globally, it's tidal motion, it's wind motion, it's earthquakes thousands of kilometers away. And what they do is they set up these very low frequency vibrations, but very high energy vibrations that then travel slowly to great depths over vast distances. And because it's such low frequency, we can actually get depths of hundreds of meters with a relatively small layout of geophones. So what does a shot record look like? Well, here's no surprise. An active shot record looks exactly the same as an individual shot record from reflection or refraction survey. So here's one where the shot has been at the end. And so gradually through the spread, the arrivals get later and later. And what we're interested in are the surface arrivals. So they're the big ones. And as I say, what's happening in the background is quite complex, but actually in the software, the processing is relatively simple. So we load our shot record in, single shot record, and the software will run dispersion analysis on it, and it will give us a plot of the phase velocity. So this is the phase velocity across the top, and then the various frequencies down below. So it's telling us how fast the different frequencies were able to move. And what the software needs us to do is just quite simply pick the biggest value for each frequency. And it's as simple as drawing a line through the center of this plot. We then give that dispersion curve to the software and it runs an inversion. So exactly like resistivity, exactly like refraction, it tries to find a model of the ground that would produce the same dispersion curve. Simple as that. So this kind of separating out frequencies, the analysis of all that, complex but happening in the background, and we are just drawing the line through here. And so down the side, this is what you would get output from a single shot record, is a single profile of velocity against depth. And you can see as this is active, our dispersion curve goes down to just beyond 30 meters. And you probably find that that last point is, you know, getting a bit questionable, but that allows us to build our model. We can then take lots of shots, and that then allows us to build the 2D profiles, or as I say, 3D volumes. So talking about the instrumentation itself, what are the highlights? Well, again, as with all of ABEM's instruments, it's the versatility. You know, we have a system here that can measure, in terms of the frequencies it can measure, it can go up to 20 kilohertz, but it can actually measure a flat response, 0 hertz DC signal. That means that it doesn't matter what frequency of vibration is coming in. It doesn't matter whether you're close or far away from your source, you will still be able to represent that seismic signal accurately. We have a time window of 480,000 samples. That's an incredibly long time window. We've got a very small minimum sampling interval. So that means that you can have incredible accuracy, incredible detail. And really what it boils down to is that it means that there isn't a method that we can't do. So whether it's refraction, whether it's reflection, whether it's surface wave, borehole, the system can cope with it. It's also a nice compact system. We don't have an external laptop. Everything, like with all of the ABEM instruments, is built into the instrument itself. So there's no no requirement, as this poor person had to do, of putting a computer in a plastic box because it might be raining a little bit. We just have one unit, IP66 rated. So as with all of our instrumentation, capable of withstanding high pressure water jets and entirely dust proof. And we've tried to make it as simple to use. So it's got a nice kind of friendly graphical user interface. And we have like an A to Z map. We have a wizard mode when you start it up that will help you to set the instrument up for the particular method that you are using. So let's have a look at some case studies. So this first one is a refraction study. This is looking for bedrock strength. It was a massive infrastructure project that was running through Sweden and Norway. And it was upgrading both rail and road route, and required a lot of tunneling. So there was, ahead of the tunneling, a lot of refraction surveys. Some of it was done over water, some of it was done on land. And this is just one of their survey locations where they had to tunnel through a hillside. And their aim is to understand where the bedrock might be weak, and therefore where they might need to use some kind of remediation to support the tunnel where the bedrock wouldn't be able to hold itself open. So this is their refraction data set over a few hundred meters. And they had a fairly simple interpretation here, which was where the velocity suddenly increases, that is interpreted as being the top of the bedrock. And then once you're in the bedrock, what you're looking for is variations in velocity. And they could see very clearly that there was this sudden break in the bedrock where the velocity dropped, and they interpreted that as a fracture zone. You know, a lot of fractures in the rock, and therefore when you were tunneling through that, there is the potential for collapse. And also a discontinuity, where you wouldn't expect to see this kind of strange offset in the bedrock. And so that probably implies that there is some kind of fault line there. And it's probably that fault line that has caused the fracturing in this part of the bedrock. So again, just gives them an early warning on what they might expect when they get into the tunneling. This is a paper that I saw published just this year, and I threw this into the presentation at the last minute, just because I thought it was interesting, because this is data that was collected in 2000 with one of our seismic instruments and actually reprocessed this year. So 20 years apart, the processing and the data collection. But this is 48 channels, so that's can give you a pretty good detail along your profile. And with the Terralog, we have a 48 channel instrument, we have a 24 channel instrument, and we have a 12 channel instrument. Number of channels is the number of geophones that you can add to it. Now in this instance, they didn't have a 48 channel instrument, they actually linked two of them together. So they had two 24s, interlink them, and you can then use them as a single system. And this was actually using a predecessor, like a Mark 6 Terralog, I think, much older one, but still good, reliable instrument. And what they were trying to do was they were trying to map the bedrock. They were identifying fault zones within the bedrock, and then looking at the overburden materials that lay over that bedrock and defining what they were. So they were getting the layers from the sort of this raw reflection plot, and then they were making the interpretation based on the velocities that they had managed to get through velocity analysis of this. And then looking now at MASW, at a surface wave method, I thought I'd look at VS30 because this is a really interesting one in terms of site evaluation for building, because this is a methodology that has been set up in the kind of engineering documentation as a kind of set method. You follow a procedure to get a given result on a site. So because you're following a set procedure, it means that everyone collects the data and processes it in the same way. It means that you can then compare your result against a predefined set of criteria to give you an answer about how stable the ground you're about to build on is. And this got put in place as a result of something called the National Earthquake Hazard Reduction Program that was set up in the 70s. They said that before building, specifically in earthquake environments, you should analyze the shear wave velocity in the top 30 meters, or if you work in old money, the top 100 feet. So sometimes it's called VS100. And if you can classify what the average shear wave velocity is in that top 30 meters, you can then grade the site in terms of its suitability for building on. And that is included in the International Building Code. So previously, the way to determine the shear wave velocity for that top 30 meters was to do invasive tests, but now we can use surface wave methods to achieve it. So to say, the field procedure is laid out very specifically in the documentation, tells you what you should do. So it says that you should be using 12 or 24 geophones with a spacing of 1 to 2 meters. You should stack between 1 and 5 times, i.e. repeat each shot 1 to 5 times. You should have a record length of 2 seconds, and that you should sample at a ½ millisecond interval. It then tells you where your shot positions should be. So it says you should take your interval and then multiply that by 1, 6, 12, and 24, and that will give you the offset from the end of each line where you need to take a shot. So if you have a 1 meter spacing, it's nice and simple. It's 1, 6, 12, and 24 meters. So you then have 1, 2, 3, 4, 5, 6, 7, 8 shot records. You put that into the processing software. You generate a profile for each of them, and then you take the average from those 8 profiles. Once you've got that, you then take the average velocity from top to 30 meters, and you compare it against the published table. If it's an A grade site, the velocity, shear wave velocity, should be above 1500 meters per second. And then gradually the grading drops as the shear wave velocity drops, i.e. the ground becomes less stable, until you get to a point where building would definitely not be recommended without remediation. The idea was to standardize the field procedure, but also to make it more simple for people to understand so that you could present the results to non-geophysical audiences. And so quite often you'll see the results like this in a kind of diagram, and the color of the box and the letter tells you what the grading of the site is. That's based on the average velocity, which is given in the table at the bottom. And then the true velocity profile, the velocity at all the different depths, is shown by the line. And because it's an average velocity, that means that you can have a site, for example, like the middle one, where 20 meters of the site has very high velocity, you know, over the 1500 meters per second, but the top 10 meters is terrible. And you definitely, therefore, wouldn't want to build, because although in an earthquake event, the bedrock would be nice and stable, this top 10 meters would shake like a jelly. So this, using the average, then allows you to downgrade sites, even if it's only a small proportion of the site that is unsuitable. Okay, that's we've done the resistivity and we've done the seismics. I'm just going to have a quick scan through the chat and see if there are any questions. And if there are any right now, please add them in. I don't think there's any questions that I haven't already answered. So what we're going to do is we're going to take a nice 20-minute break now, because I've been talking for quite a long time. And then we'll come back and we'll start on TEM, and then we will have the GPR section. So this screen will count down once it gets to 10 minutes. So it will say 20 for the next 10 minutes. Then it will say 10, 9, 8, 7, 6. So if you leave this on your screen, you'll know how long it is before I start again. If you've got any questions that you think of during the break, just type them into the chat box. And when I come back before we start again, I will answer those. So thank you very much for listening so far. I can see a couple of people asking about videos. Yep, this is all being recorded, so you will have access to that. And I'm going to go and grab myself a cup of tea. So I will be back in probably a bit less than 20 minutes now. Thanks, everyone. Okay, we are back live again, and hopefully you've all had a good break and are refreshed and ready to go. So, as I said, we're going to crack on with TEM to start with, and then we're going to move on to GPR and follow the same kind of pattern that we've done with the other methods so far. So I'm just going to get rid of my face. There we go, so that I don't cover anything important up. So the ABEM Walk TEM. This is our transient electromagnetic system. And the theory of walk TEM, or TEM in general, what we're trying to do is we're trying to generate a 1D resistivity profile. So effectively what we want out of this is the same output from a VES measurement. It's just that with a TEM measurement, it's much faster and it's much more sensitive to conductive bodies. So it's excellent for water prospection and mineral searches. So what do we do? Well, a kind of typical layout here is that we have a transmitter loop that's in red around the outside. And then we have one or two receiver loops that we put in the center, or we can put them offset, but basically we have to have a transmit loop and a receive loop, and they will be attached to the instrument. What we do is we run a current through the transmit loop, and it's a constant current. And while that current is flowing constantly, a magnetic field is set up. And that magnetic field is shown in this diagram by these yellow lines. And if we very, very quickly then switch off the current in the transmitter loop, what happens is that magnetic field collapses, and the changing magnetic field generates eddy currents in the ground. So the eddy currents are shown by these sort of orange circles, and they extend down and out a bit like smoke rings, excuse me, a bit like smoke rings into the ground. And when those eddy currents are flowing in the ground, they are generating their own magnetic field, a bit like the transmitter loop was doing at the very beginning. And so once that current is switched off, the eddy currents start to flow. They generate this secondary magnetic field, and it's that secondary field that we are trying to detect with our receivers. In reality, what we're doing is we're switching that current on and off very, very quickly. So we're setting up the magnetic field, collapsing it, setting it up, collapsing it very, very quickly, and doing it forward and backward, the same as we did with resistivity, to avoid any drift in one direction or the other. A bit like IP, we measure the time for the decay of these secondary fields in time windows, because again, these are very small signals that we're talking about. One of the difficulties with doing a TEM measurement is trying to be able to map both things that are very close to the surface and things that are very deep. And the reason for that is that if you want to go deep, you have to have a very high current. Problem with having a very high current in your loop is that it takes a long time to switch that current off in the transmitter. So let's have a look at what's happening. So this is what our current pulse would look like. This is what the instrument is trying to set up to do the transmit period. So we've got current on the y-axis, we've got time on the x-axis. We switch the current on. We let it stabilize, we leave it on to get the magnetic field built up, and then we switch it off as quickly as we can. Problem is, we can't start measuring until all of the current has disappeared from the transmitter loop. The reason being that the signals we need to record, that secondary field, is so very small that if there's any current still flowing in the transmitter, it will swamp the receiver. It's impossible to instantaneously turn the current off. If you imagine having a hose pipe with water flowing through it, if you switch the tap off at one end, water continues to flow from the other end until you know, everything has passed through the pipe. So it's a bit like that. We can't switch it off instantaneously. So we have this off ramp. We have this time while we're waiting for the current to disappear. And that bigger the current, the deeper we can get. But the bigger the current, the longer this off ramp, the more time we have to wait before we can start measuring. And if we have to wait to start measuring, that means that we miss the eddy currents that are near the surface. So if you remember, they're spreading out like smoke rings, getting deeper. We miss the shallow smoke rings. So why don't we use a smaller current? If we use a smaller current, well, then we can switch it off quicker and we can get that additional shallow data. But the weak current, the lower current, the signal will be absorbed by the ground, attenuated by the ground much, much more quickly, and we lose any usable information at the late times. So a lot of instruments you have to set up to take either a shallow measurement or a deep measurement. With the walk TEM, in a single current measurement, we alternate between high and low current pulses. We also have a big and small receiver loop. And so the low current and the small receiver are attuned to being able to detect in great detail very near surface variation. And then the larger currents and the bigger loop allow us to scoop up signals from much deeper. And then the instrument will present us with all of that data that we can combine into a single seamless decay curve. So mapping how those secondary fields get smaller with time. And that is what we can then use to do our inversion. So the instrument is it's a bit of a simplification, but it's basically small current in one direction, switch off, measure secondary field, switch the current on in the opposite direction, switch off, measure the secondary field, then bang the high current in, switch it off, measure the field, put it in the other way, switch it off, measure the field, and then just keep repeating. That's effectively what we're doing. And we're doing all of that in a single measurement cycle. So once we have our decay curve, that's the bare bones that we put into the inversion software, and then it follows that same procedure. It looks at the changing field strength over time. The software builds a model of the subsurface, recreates the survey that we've done, and tries to find a model that fits that curve for us. So let's have a look at some quick examples of TEM. This first one is in Scandinavia. This is looking for something called quick clay. And quick clay is a problem across a lot of Scandinavia. And in fact, I can't remember if it was the beginning of this year or the end of last year. It made the kind of international news when a big section of hillside in Norway just suddenly slipped away. And the cause of this is you get these layers of marine clay. So it's clay that used to be part of the seabed, and it has a quite high salt content. And when it's got salt in it, the salt adds to its structure. It gives it some rigidity. But over time, the salt can wash out. And when the salt particles have gone, the clay loses its strength. And it doesn't take very much then to initiate a slide, and the clay liquefies, and anything that's above it just shifts, and it shifts really quickly. So it's really problematic. TEM's great because TEM, as I said at the beginning of this section, is very, very good at differentiating between very low resistivity features, better than a resistivity system would be able to. And it's also very rapid. So, you know, you're talking about 6 minutes or something like that to actually collect the data. Once you've laid the loops out, and laying the loops out might take you 20 minutes. So here's an example where we've got marine clay, because of its salt content, has an incredibly low resistivity. And what the researchers here are interested in was finding where in the clay the resistivity jumps up to a value that you would expect for non-salt clay. And so they took a series of the 1D TEM soundings, and they just highlighted those regions that match non-salt clay resistivity. So you can see marine clay here, washed out clay beneath and above. So these could both be potential slip planes for a landslide at a later date. And on the left-hand side, that's the sounding curve. So that's showing how the field strength changes over time. And it's not very clear on this image, but I think the green is the raw data and the red is the modeled data. So again, kind of one of the key applications for TEM is groundwater. And this is from a survey in East Africa, and probably in some of the best conditions we've ever seen TEM used. It was incredibly quiet in terms of background noise. So that means that you can record your signal down to a great depth. And key to this, relatively resistive and homogeneous overburden or bedrock that then drops into something more conductive where the fresh water is. So they could achieve great depths, so indicated 335 and 440 meters in these models. So the models are showing resistivity along the bottom, depth down the side, and the green dashed line is where the inversion software says, below this depth, I don't trust the data. And this was collected with a 40 by 40 meter transmitter loop. So a square of wire, 40 meters each side, 2 receiver loops in the center of it, and a 12-volt car battery. And so with them, they understood the geology very well in this region, and they know the range of resistivities that would indicate that the bedrock contains fresh water. And so it was quite simple for them and fast to do a series of soundings across the landscape, pick the regions where the resistivity drops into the kind of flooded geology values, and even in some instances identify zones where the groundwater was becoming brackish and then in fact fully saline by a further drop in resistivity at depth. So that allows them to plan their wells very easily and simply based on those resistivity values. And compared to the effort it would take to do a VES measurement over these kind of depths, TEM has some very big advantages. So this is just sort of taking things to another level. This is actually taking lots and lots of TEM soundings and doing something slightly more clever with them. So each of these black dots is a TEM sounding, and you can see we've got settlement along the side of a river, and they were going to be expanding the settlement back inland, and they wanted to get a handle on how the geology changed as you moved away from that river. So what you could do in the processing software is you can take each of those soundings and you can generate a discrete profile as they've done here, or you could actually interpolate that if you wanted to see how the resistivity values vary as you move through the line of soundings. You could also superimpose onto that some kind of geological interpretation based on the values that have been returned. But they've actually gone a step further here, and what they've done is they've taken those sounding locations and they've tried to map how the resistivity changes in plan. So generate maps of resistivity at, as you can see in the corner here, different depths. So we'll just let this cycle back to the start again. So this is shallow, 10 to 20, 20 to 30 meters. And then what you'll see is that as it gets deeper, the colors disappear gradually. And that's as the depth of investigation is met, that DOI, that green line on the plot. Once it hits that, it removes the data from the plot. So you can see, you're not looking at unreliable data. You can tell when it stops being useful. So these kind of things are pretty simple. To do this many soundings is not actually a huge campaign with TEM. And then we can bring it into this workbench software, I think it was being used here, and we can model it in these different visualizations. So what's so good about the warp TEM? Well, first of all, it's a nice, simple modular design. The original warp TEM was a transmit and receive in a single box. We have a choice of antennas. So we have 2 receiver loops, small one and a big one, and then transmitter loops that vary from 20 meters square up to 200 meters square. Smaller transmitter loop is going to be good for shallow investigations, bigger transmitter loops better for depth. So you can just add on the bits that you need. As we said, it's running this dual moment, so you can get shallow and deep data all in one measurement cycle. And it's the speed of operation, really. So as I say, you're talking about less than 30 minutes. The Warp TEM has onboard inversion software. So you collect the data in the field, you press a couple of buttons, it automatically processes the data and runs the inversion. So you could get this result whilst you're still stood on the site that you took the measurement at. And basically going from this state where it's just been taken out the back of the van to this model is less than 30 minutes with a 40 by 40 loop. You lay out the outside loop, you drop the 2 receivers in the center, you plug everything in, 6 minutes to 8 minutes for the measurement, a couple of minutes for the inversion, job done. The original Warp TEM was limited to 15 amps. So that's the most we could put around the transmitter loops. However, we have an external transmitter called the TX60, and this allows you to put up to 60 amps into those transmitter loops. Now, we had a test and calibration site that we used to use a lot in Denmark, in a place called Lyngby. And with the original system, all of the measurements we had taken there, the maximum depth we'd managed to achieve was 270 meters. By using the TX60, not quite at full capacity, we managed to double that depth. So there's a lot to be said for ramping up the current from that initial 15 amps up to somewhere towards 60. The exciting news for 2021 is that early next year, we will be launching the Warp TEM 2. And this has if anyone saw our TEM webinar that we did earlier in the year, this is the slide taken out of that presentation. The great thing about the Warp TEM 2 will be that it keeps the dual moment measurements, it keeps the twin channel to have the 2 receiver loops. But what we're adding is we are going to split the receiver and the transmitter out so that you have a small transmitter box and the main unit with the computer and everything is just the receiver. And that allows us some advantages because that allows us to set up more options in terms of the scale of the instrument. You know, the price range can be broader, the specifications can be broader, but it also reduces signal noise even further than we managed to get it on the Warp TEM 1, which is exciting. We still have the onboard inversion, so you can still process your data while you're in the field. We're now going to be able to get up to 20 amps before you actually need to invest in a TX60. So we've kind of stretched the capability of the transmitters that we have. As I said, more receiver options, more transmitter options, so easier to find a system that is suited to your needs or your budget. Still got an inbuilt GPS, the same as all of the ABEM instruments, so you will always know where you were measuring. And one for anyone who's actually done a TEM measurement, you'll know that you tune the transmitter circuits by adding a damping resistor, and that allows us to get the best possible transmitted signal into the ground. That always used to be an external device, and we didn't have a way of knowing really which was the best one. You had to use experience. But now we're putting those resistors internally, and the instrument will actually assist you in picking the correct resistor for the site that you're on and the loop that you're using. So it makes taking measurements far easier and far more reliable. And we can also now record not just the Z component, so not just the vertical component of that secondary magnetic field, but also X and Y. And that's excellent if you're looking at 3D bodies, such as mineral deposits. So really exciting time beginning of next year. And if you want to know more, I'm sure Mustafa can fill you in. So that's TEM. And now we're going to move on to the last section, and that is the MALÅ brand, our GPR system. So ground penetrating radar. How does ground penetrating radar work? Well, it's a radio frequency system. We use electromagnetic waves in the radio spectrum to transmit energy into the ground. So radar stands for radio detection and ranging. So it basically is, it was designed in the first instance for looking for aircraft. So the idea was you could detect an aircraft and you could get the range, the distance to it. So radio detection and ranging. But then we decided, oh, do you know what? It'd be a good idea if we turned that instrument upside down and transmitted it into the ground. So the instruments fire pulses of electromagnetic waves, pulses of radio waves into the ground. And those radio waves travel through the ground uninhibited until they reach some kind of interface. And that is somewhere where the electromagnetic properties of the ground change. So a lot of people compare GPR to seismics, but seismics, you're talking about physical characteristics of the material changing, like the density, the rigidity. But with GPR, we're talking about electromagnetic properties changing. So you can have two materials that might have a very similar seismic characteristic, but would still give you a very strong GPR response because their electromagnetic properties are different, or vice versa. Something that shows in seismic could conceivably not appear in GPR. So it's electromagnetic properties we're looking for a change in. And what we're doing on the ground is we have a transmitter and a receiver. Here they're shown separate, but quite often they're going to be in the same box. The transmitter starts to fire energy into the ground. It also fires a bit of energy above ground. It's very difficult to shield an antenna 100% without causing a lot of internal noise. And the energy that travels through the ground is moving at about a third of the speed that the energy travels through the air. So energy traveling through the air moves at roughly the speed of light. Energy in the ground, approximately a third of. That means that the first thing that our receiver detects is the energy that has moved through the air. So we get this big pulse, direct wave from transmit to receive, air wave. The next thing it gets is the direct ground wave, direct from the transmitter to the receiver, not reflected off anything. And then we get maybe a bit of a quiet zone whilst the energy propagates through the subsurface. When it gets to something that is different, we get a reflection. Like reflection seismics, the bigger the contrast in the properties, the bigger the reflection you'll get. The energy starts to come back towards the surface, and when it gets to the receiver, we get a hit. So in the old days, all we used to do was we used to plot a series of these traces. So we transmit, receive, move, transmit, receive, move, transmit, receive, and build up our picture of these wiggle traces. Now, unlike reflection seismics, we don't have to do too much complex processing because we effectively have the transmitter and receiver in the same place. So we are just seeing the reflections in their true positions. These days, what we do is we apply a color scale to this wiggle trace. So white if it's pointing out in positive direction and black if it's in the negative direction. And we drag our instrument or push our instrument or tow our instrument or fly our instrument across the surface. And each one of these traces gets plotted next to each other and we generate a radargram. One thing that's very common in GPR data is the hyperbola. And we'll look at these in real data in a minute, but it's this kind of upside down U shape that we get from features. And it's kind of one of the bigger issues with doing GPR survey. And that is that the instrument doesn't look directly beneath it. The energy comes out from the transmitter and it immediately starts to spread out in the ground. So it doesn't just go straight down in a nice pencil thin line. It gets broader and broader and broader as it goes. And that means that the instrument is actually sending out energy slightly ahead of it and slightly behind it. So if we look at this example here, when the instrument is at this location in red, the energy is spreading out in all directions. And so it is possible to get a reflection from a feature that is not directly beneath the instrument. Radar systems aren't clever. Radar systems just record the strength of the reflection and the time it took for that reflection to arrive. So as far as the instrument is concerned, that reflection is coming from directly beneath it. So that is the only place it can plot it. It doesn't have any other information about where that energy has come from. So it takes that reflection, it takes that time from this distance traveled, and it plots that into the radargram trace down there. When you're directly over the top of the feature, as shown in blue, everything's much simpler because the energy is going straight in, it's hitting the target, it's coming straight back out. So that offset time, that time for the travel of that distance is correct, and the reflection is plotted in the correct location. Afterwards, once we've moved past the target, we have the opposite problem. We've now got the energy that is spreading behind the instrument, also getting a reflection from this target. And again, because the instrument isn't clever, it just sees reflection strength and time. It has to just plot it where it's positioned. So you end up with this hyperbola. You get this distorted shape, which fortunately in the processing we can correct for. If we know what the velocity is, we know how far the instrument will have been looking ahead and behind. And so we can correct these back into their correct positions in the post-processing. With the GPR system, we touched on frequency when we were talking about seismics. It's even more important in GPR because we're talking about kind of compressed depth of survey. The attenuation effects with the frequencies we're talking about are much faster. So it's really important to get the right frequency for the job we need to do. If we use a high frequency antenna, the signal is oscillating very quickly. And that means that we can detect things that are quite small. We can detect layers that are quite thin. The problem is that it's oscillating so quickly, it uses up energy very fast and it gets absorbed or attenuated very quickly in the ground. If we use low frequency antennas, then the oscillations are slower, the energy is not used up as quickly, the energy will get, the radar waves will get further into the ground before they're lost. But we lose detail. So this is a profile taken over the same patch of ground with two different antennas. We have a 500 megahertz on the left and a 250 on the right. And what we can see in the 500 megahertz data is that this reflector down here, this hyperbola, is only just visible above the background noise. So that's coming from television, mobile phones, radio, lightning storms, all sorts of things contribute to electromagnetic noise. And the signal is getting attenuated faster and faster, and the instrument is having to turn the volume up to be able to see these deeper signals. And the problem is when it turns the volume up, it also turns up the noise. So you can see that this is only just visible. If you look at the 250 megahertz data, it's clear as a bell. We're not seeing the background noise because there's more energy in the ground. The instrument doesn't need to turn the volume up as far on these deeper signals. However, the other side is you look at the detail that we've got on these shallow features here, 1, 2, 3, 4, 5, and then look at the 250. It's nowhere near as clear. We're starting to lose the clarity, especially up here. And so that's the payoff that we have. We have to decide what is more important, or we have to use more than one frequency. We also need to consider our capability of being able to detect objects of certain sizes at depth. And this is difficult because as you get deeper, as I said, the energy starts to spread out. So the footprint gets larger, and gradually the higher frequency component gets absorbed, and you're just left with lower frequencies. And what it means is that we can only see small objects when they're near the surface. And as we get deeper, features have to be bigger or thicker for us to be able to detect them. Now, the true kind of resolution of a system is going to be very dependent upon the material that you're working in. If you're in a material that is absorbing the signal very quickly, then it's going to be different from if you're in a nice resistive sandy material, for example. The rule of thumb that you can use is that the size of the object shouldn't be smaller than 1/10 of the depth, 10% of the depth. So effectively, if these are meters down the side, if you're at 6 meters, the object needs to be 1/10 of that to be detectable, so 60 centimeters. If you're at 1 meter, 10 centimeters. So as I say, sometimes it will be worse, sometimes it will be better, but that's a good approach to use. Now, by and large, this is not related to instrument manufacturer. This is physics that defines this. The frequency of the antenna, the resolution that you get out of a given frequency, and the resolution you can expect at depth are controlled by physics. And it is very difficult to break the laws of physics at present. And so these kind of rules of thumb don't apply to just us, they apply to any GPR system. We're also massively constrained by the type of material that we're working over. So if we're on very conductive soils, we will struggle to be able to measure with the GPR. So for example here, this is a nice sandy soil, very low salt content. So salty sands are terrible because they're very conductive. This is a clean, dry sand. We've got excellent penetration down to 8-9 feet, something like that. And everything's as clear as a bell. Here, we've got a really conductive clay soil. Clay is incredibly conductive even when it's dry, let alone when it's wet. And we're seeing nothing. We're just getting these very strong ground effects. Basically, all of the energy is just sat in the very top foot of the surface, and we don't get anything from below. And there really isn't much we can do about this. If you could just wind the energy up on the GPR, you still wouldn't get a huge increase in penetration. All that would happen is you'd be sending even more signal through this top layer. You'd just be warming it up. That's all you'd be doing. And even if you tried to use a lower frequency antenna, you'd still find that the conductive nature of a soil this bad, it would still just be sat in those very top layers. So there are some limitations to GPR. A lot of people just kind of see it as this wonder tool. A lot of people try and sell it as a wonder tool, but it does have limitations, and you need to consider them before you start your survey. So firstly, penetration depth and our ability to locate a target at a given depth is very strongly dependent upon the soils on site. If it's very conductive, i.e. there's clay in there, or let's say there's saline groundwater, then you're not going to be able to get a good result, no matter whose instrumentation you use. You need to have a good contrast between your target you're looking for and the host material in which it lies. Now, this is no different from any geophysical method. All geophysics relies on contrast. You have to have a difference in the property that you're able to measure between what you want to detect and what is around it. And if there isn't, you won't see it. So always think about that. And the final one is interpretation. And again, this isn't unique to GPR. This is geophysics in general. You know, you can learn to use an instrument very quickly, but learning to interpret the data is really only done by experience. You can fast track it by reading journals and talking to other people, but it's tricky, and it's a steep learning curve on any method that you use. So experience of interpreter is difficult. No manufacturer as yet has designed an instrument where you can dial in what it is you want to detect, press a button, and it will tell you when you walk over the top of it. Physics doesn't really allow us to do that. So let's have a look at just some examples. A lot of that data that we looked at when we were talking about the theory were hyperbolas, and they will have primarily been from pipes or small targets. So here you can see a series of pipes. You can actually see a cut for the edges of a trench where a larger pipe has been put in. And with this sewer pipe, you actually see a reflection from the top and the bottom of the feature. I mean, kind of typical types of response that we might see apart from hyperbola, so we might see an effect called ringing occasionally. So this is something that's quite common with radar data. If you get something that's very high contrast, then the very high contrast means that a lot of energy then gets sent back up to the surface. And the thing you need to remember is that GPR energy works the same regardless of whether it's going up or whether it's going down. So it goes up to the surface, and there is a big contrast when it reaches the surface. So if you reflect a lot of energy up, when it gets to the surface, you actually reflect some energy back down again. And then it gets to this very reflective surface, and you get another reflection back up to the top. And this repeats over and over again, but gradually with sort of less and less energy each time, and you get this kind of repeated pattern. And so it's very important to be able to recognize that for two reasons. Primarily so that you don't confuse your interpretation and say, oh, well, I think there's a number of different features, one above the other here. True. And the other is that it can be indicative of these high contrasts. So it might suggest that you have a metal body, like a metal pipe, or something with a void in it, which gives a very high contrast between the geological material or the building concrete material and the air gap in it. So it can be really a useful thing to identify. You'll see planar reflectors. So rather than a small feature that just gives us a little hyperbola like we've got here, a flat reflector. So that could be a surface, or you could be running along the top of a pipe. It's very difficult to say from just a single radargram. But here we can see we've got a planar reflector, and actually enough energy is getting through that reflector to show us features beneath as well. So this one is just partial. This is, this could possibly be kind of the GPR coming onto a section of pipe because we're not really seeing the reflector at the far end. You can get continuous reflectors. So this could be in, for example, road scanning, where you're interested in the contact between the base of the asphalt and the road bed material, or the road bed and the natural geology underneath. It could be mapping ice thickness. So you want to see where the bottom of the ice is. Anything where you've got this continuous surface. Top of bedrock, if it's a very clear, clean contrast between the overburden and the bedrock, then you might be able to do that. Or mapping the underside of a concrete slab. How thick is this slab? So continuous reflector, very easy to interpret and pick the depth at different locations through the data. Quite often, though, depending on what industry you work in, quite often, what you're really looking for is just a change in character. You're looking for where the background deviates, or something deviates from the kind of normal pattern of response. And so that could be an increase in reflection strength, which could indicate that you've got debris or pockets of air. It could you could get a loss of signal, which might indicate an increase in water, so conductivity has gone up, so around a pipe that's leaking, something like that. You might see more ringing that indicates that there's a void developing, or you might just see a very marked difference in the penetration depth. So you suddenly come onto somewhere where it's more resistive, and actually you can see features much deeper, and then it comes back up to the surface, towards the surface where it's more conductive. So it can tell you something about the materials beneath the antenna. As I kind of touched on when we were talking about the planar reflectors, it's very difficult from a single traverse to be able to identify exactly what the feature is. So if I have this single radargram, I would not be able to tell you for certain whether this was a pipe or a void or a rock, a single item, a confined feature that's causing this reflector, because I have no idea what is happening to the left or to the right of the line that was collected. But if you collect parallel traverses at a particular interval, then you can start to map whether or not features are continuous between the traverses. And that then allows you to start to define the size of features. And we can actually take that on a step further, and we can collect our parallel traverses, or they don't have to be parallel, they could be collected with a GPS or a total station, kind of wandering path. But we can take all of those radargrams, we can put them together and build a volume of data, and then we can slice down through the data from top to bottom and look at how the reflection strength varies in plan, like as a map at different depths. So here we can see an animation of reflection strength across the site looking from the top, and this is just cycling from top to bottom. And we can see a combination of things like potentially, pipe work. There's a pipe running through here. There it is. We've got building foundations in here, and we've got natural responses like paleo channels or something beneath all that running through this section. So let's have a look at the products. We have quite a lot of radar products. So we'll take them one at a time and we'll just briefly discuss what each is suited to. So let's start top right. Let's start with our CX. So CX is short for Concrete Explorer, but it can do quite a bit more than just concrete. It's a high frequency system. So it's excellent for inspection of concrete, whether that's slab thickness, checking for delamination. We can do rebar mapping, looking for pipes and cables, just structural investigation. You can look at the kind of state of a structure, whether it's looking at stone cladding on a building, seeing whether it's starting to separate from the main structure or not. And also used by sort of security and police forces to look for hidden evidence, buried weapons, things that might be concealed in a wall, stuff like that. So it's very easy, simple to use unit. It has interchangeable high frequency antennas. Here you can see we're just doing a bit of mapping of some the concrete slab in our office. And we can get really quick results from this because we can process it on the screen. So here we can see there's actually where this was measured. It's a joint between two sets of rebar mesh. So we've got one set here and one set here overlapping through the center. So that's a top-down view at a particular depth. This is a side-on view of one of the radargrams. And so you can see these red lines show us the thickness of the time slice that we're looking at on this side of the screen. So really fast way to get a result. The GX, this is our ground explorer. This is an instrument that has slightly lower frequency antennas and is used for a range of stuff from engineering to archaeology to road and rail scanning, pipe and cable mapping. It's basically a kind of suits all type of instrument because we have a range of frequencies on the antennas from 80 megahertz in the lowest up to 750 on the higher. So a good mix of deep penetration to high detail. And also this system has what we call HDR technology in it. So that's high dynamic range. So I'm going to just briefly explain what that means. In a traditional GPR system, the way that we build the trace, that wiggle trace, is that for every sample we want in the trace, every point that we plot in that trace, we fire the transmitter once. So fire our transmitter, out comes the pulse, and we get a single point on the trace. We measure at time, let's say 1 nanosecond. Then we fire the pulse transmitter again. Now we get our second point in the trace. Then we fire the transmitter again and again and again and again and again and again and again. And we build up very slowly this trace that we want to see. So if we have 300 samples down the trace, the transmitter has to fire 300 times. Now, fortunately, GPR, radar energy is traveling at 1/3 of the speed of light. So it's pretty quick to be able to do this. The repetitions are quite fast. However, with the HDR system, we move towards real-time sampling. So now we fire the transmitter and we actually record at more than one location, more than one offset time. And then we fire the transmitter again and we start filling in the gaps. Fire the transmitter again, fill in the gaps, fire again, fill in the gaps. And now what we do is we end up with a result with fewer transmitter pulses and greater detail at the end because we can have more samples for the same amount of time, or we can keep the same number of samples and we can stack lots. We can repeat the measurement over and over and over and over and over and over again. And if we do that, Random background noise gets minimized, it tends to cancel itself out, but the true signal gets superimposed and gets stronger and stronger. So we improve signal to noise ratio. Given that the background noise and signal strength are what control how deep we can see, then that's going to control how well our antenna is going to perform. So a GPR antenna isn't just really a single frequency. It's this wide bandwidth of frequency. So if you looked at the spread of frequencies that come out of the bottom of an antenna, you would see that they range from very low frequency to very high frequency. And the middle of the peak is the value quoted on the instrument. So say this was a 750 megahertz antenna, that center point would be 750. Down here might be somewhere around, I don't know, 300 megahertz, and this would be somewhere around 1000 megahertz, something like that. The low frequency component is giving you your depth penetration, your high frequency component is giving you your detail. And once the energy, the strength, the amplitude of the signal falls beneath the noise floor, we can't use the data. So if we can push that noise down by stacking the instrument, the measurement lots and lots and lots of times, then we actually increase the bandwidth. So if we have more low frequency, we can get deeper. If we have more high frequency, we can see more detail. So with a single frequency HDR antenna, we manage to reduce the noise floor by this ability to stack many more times than was previously possible. And it means that we actually get very similar performance from a single frequency HDR antenna as you would get with a dual frequency traditional GPR design. And this is something that we had a lot of trouble trying to persuade people. So we spent a lot of time doing head-to-head comparisons, and we're always happy to do these. So we can turn up on site with a single frequency HDR, and you can put it next to a dual frequency old style antenna. You can run them both together, and you'll see that you don't get anything more from the more expensive dual frequency system. In fact, the downside of the dual frequencies is that you usually get a bit of a dip between the two center frequencies, and quite often it's a useful frequency that you might want. So HDR is really kind of changed the game in terms of data quality and the depths that we can achieve with any given frequency. Advantages of the GX system is that we have Wi-Fi control on it. So you don't need to be stood next to the antenna. So here you can see I was in a mine and they were looking for weaknesses in the rock. I wasn't allowed to go up in the cradle, but that was fine. I stood back with the antenna, with the receiver unit, the console, and they just used the transmitter and receiver unit on the wall, and it transmitted via Wi-Fi. And if it loses the Wi-Fi connection, the antennas will record continuously. And then as soon as the connection is remade, they buffer all of the data across, so nothing is lost. There are loads of configurations. We can't, not just the different frequency antennas, but the way that we deploy the instrument, whether it's being dragged over the ground, towed behind a vehicle, in a rough terrain cart, or a very small rough terrain cart that allows us to put the smaller antennas into it. And just this year, we actually launched our GeoDrone, which is based on the GX technology. And this is an 80 megahertz airborne antenna, which is suitable for multiple different environments. So you can see here examples of data collected over sand and peat, so that's an organic soil, over ice and over water. And this is fresh water where we're mapping the riverbed. So here the drone has flown across the riverbed towards the bank, turned around, come back across the riverbed. So this is really great for being able to get into environments where it might not be safe or practical to actually have an antenna on the ground surface. And so, for example, with this water measurement, we could just fly a long looping path. We could then pick the bed response from the data and then model in 3 dimensions the shape of the river channel without ever having to get our feet wet. So let's just have a look at a couple of case studies with the GX type instruments. So here, this is an inshore sediment example. So this is putting an antenna in the bottom of a boat. and then mapping the both the sediment surface and the bedrock beneath it, and in fact features that are buried within the sediment itself. So of course this was done the hard way before the geodrome was invented. So this is going out with a boat with a GPS on it, but now we could do this just by flying the system across above the water surface and get a similar result. This is an example on a levee where you can run the systems across the top of the levee. They were worried that they had animals burrowing into the bottom of the riverbanks, the protective bank that stops the river from flooding. And so again, this is the example we talked about where having multiple traverses allows us to make sure that we have, that they really are continuous features, therefore likely to be animal tunnels rather than an isolated target. This is an interesting one. This is looking at the ballast on a rail track. And so with this one, this was a pilot study, so everything was kind of made up just to test whether it would work. But they were using the GX160 antenna on either a real train or just a hand cradle. And all they were doing was mapping along long sections and just, as we talked about before, just looking for wherever there was changes in the pattern of response. They would then record in a table the distances where they saw these changes, which then allowed the engineers to go out and inspect the railway ballast in those locations. Really fast to do the data collection, really fast to do the interpretation. Basically can do it in real time whilst traveling along the track. So related to the GX is the Easy Locator. This was a system that was designed primarily for the utility mapping market. So this is kind of fixed frequencies on the antennas. The small one is the 450 megahertz antenna, which is kind of the sweet spot for doing utility mapping and shallow obstruction void location. The antenna is fixed in the system. It's a foldable frame, so it's easy to get it into the back of a survey vehicle. Right, so where did we get to? So we were talking about the Easy Locator. Very simple, easy to use, good interface on it for being able to rapidly mark up stuff whilst you're still on the site. As I say, the center frequency of the small one is 450 megahertz, but we also now have the wide range antenna that is actually dual frequencies. That's dual frequency and HDR. So this is kind of having the best of both worlds. We're really spreading the bandwidth, giving us very deep penetration and very good near surface resolution. So the Pro-X is our professional explorer. This is the kind of universal unit. This can do pretty much anything, and it's modular, so we can just bolt on attachments to pretty much allow it to do anything from very low frequency like snake type antennas, unshielded antennas again for low frequency geological work, the high frequency antennas like we have on the CX, borehole antennas, shielded antennas, so for kind of regular engineering type work, geological work, and then a custom setup. So just having antennas that are built into systems for bespoke requirements. And one of those kind of specialized uses of the Pro-X hardware is our multi-channel mirror system. Oh, I've got a couple of case studies. I've thrown myself here by being disconnected. So yeah, the Pro-X allows us to do multi-channel survey, so we can have multiple frequencies at the same time. And one of the key things that can help with is road scanning. So you've got a high frequency antenna at the back that's mapping asphalt thickness and looking for defects within that. And then a lower frequency system that can look at the deeper material. And we can have up to 8 antennas on a Pro-X unit. So that's can give us a multiple frequencies, or like if you're doing rail scanning, you can have same frequency center and outside of the ballast piles. It's up to you really. It's very flexible. And so then we can take that system, and we could just map the asphalt thickness with red for thin and blues and greens for thick, showing where there's unlikely to be any issues in the future. Using the bedrock system, using the RTA system, this is mapping bedrock. So this is for a developer who wants to, before they take a purchase option on the land, they want to know how much they're going to have to spend trying to put foundations in. And if bedrock's close to surface, then it's a very easy job. So they were using the low frequency unshielded RTA. This is a snake type antenna, so it's very easy for one person to use. ProX in the backpack, GPS antenna, and then you just walk with the antenna towed behind you on a belt. So it's very quick to collect data, very easy to go through, digitize where the bedrock surface is, and as you do the digitizing, then you will have your X and Y coordinates automatically assigned to those picks, and that allows you to then plot either just a table of results in terms of where the depth to the bedrock, or actually do it in a more graphical way so that you can see a data plot of the depth to bedrock. And of course, we can then export those to other things like Google Earth or GIS to combine with other engineering data. This is, again, just bedrock survey. This is looking for limestone cavities with a low frequency antenna. So you can see we're looking at a maximum depth of about 12 meters here. And these are these karstic features, these solution holes in the limestone. And again, more with these low frequency unshielded antennas. The limestone is relatively homogeneous, so you don't see any reflections apart from where we've got these voids developing. The ProX does give you the option to actually achieve the unbelievable and get very high resolution at depth, but that does require you to use a borehole antenna. So you drill a borehole or use an existing borehole, you drop your antenna down, and then you can get good resolution because you're actually measuring the features where they occur rather than trying to do it from the surface. The only thing you need to consider is that if that borehole has a metal casing, you won't see anything. All of the GPR data will be, GPR energy will be reflected. And as I say, at the heart of the ProX is actually at the heart of our original MIRA system. So MIRA stands for MALÅ Imaging Radar Array. And this is where we have a large number of transmitter and receiver units in a single box that allows us to collect data in a very dense pattern. And that allows us to pick out incredible detail in the results. So we have a choice on the original MIRA of 200, 400 megahertz or 1.3 gigahertz. So this is normally for kind of asphalt, bridge deck type studies. This is normally for kind of engineering and archaeology and utilities. And then this lower frequency one tends to be sort of engineering and geology type applications. It's true 3D data. So we have equal spacing between our survey lines that come out of the box as we do inline, which means that when we process the data, we can look at it in any direction. We can create radargrams across a feature in any direction. We can customize how many channels we have in the box. So we can have either small or large units. And we can customize how we shoot between the transmitter and receiver. So we don't need to use the nearest two transmitter and receivers. We can actually transmit from one side of the box right across to the other. So this is just an archaeological data set I collected in my previous survey life. This is over a Roman settlement. And what we can see is we've got foundation materials, we've got floor surfaces, we've got pillar bases, and we've got this level of detail that we just wouldn't be able to achieve with a single channel instrument, pushing it up and down, up and down. So with this, we can have a box towed behind a vehicle, and that allows us to collect a data set like this, which is about 90 meters by 45 in about half a day. New for 2020 is our mirror HDR. So we've taken this concept of having lots of antennas in the box, lots of detail, and we've applied the HDR technology to it. So improving penetration, improving detail. So bringing sort of new levels of quality to the data that we can collect. Again, like the old mirror, we can deploy it in tow, push, or even hand deployment. At present, the basic system is a 500 megahertz, but HDR, so kind of stretches the legs of that frequency. 22 channel system, so 22 lines of data come out of the box. We've got much better ability to customize, even more than we had in the original system. And we've improved on the acquisition software. So not only do we get a live readout of where we are on the ground so that we can see exactly where we've collected data, we get the radar profile from any one of the channels. We also get a live time slice. So we can look at the amplitude map at any depth whilst we're collecting. So we can see stuff in real time. Fantastic development, really exciting product. Really pleased to see it out there on the market now. So here's a couple of mirror case studies. This first one is over an airport runway. Limestone geology, they were looking for sinkholes. You really don't want a sinkhole underneath a runway. This was using the original mirror. Using a GPS, you can just about see it there on the instrument. And this was all done in a day, data collection and processing. So this is the runway. They've had a previous sinkhole open up, which they had repaired, and we'll be able to see that in the data. So this is a time slice of reflection strength at approximately 1.45 meters below the ground level. And what you can see is the limestone is relatively homogeneous, so you don't get many reflections back. You can see here a ring of reflection from the edge of the previous hole that has been backfilled. So you get a reflection from that edge. But we can see these other two regions where we've got strong reflectivity. Now, there's no sign at the surface of anything. So this is probably the development of voids within the limestone that are going to turn into a sinkhole. So this is just an animation of it. There's the original one that's been backfilled. And now we can see in the limestone, these two areas are going to start to show up that look like they might be problematic. And so, of course, the engineers can then go and look at those in more detail. And if we actually do a cross-section on them, we can see that, yeah, we've got this relatively homogeneous limestone, and then this increase in reflectivity that is cause for concern. Utilities is the other big use of the mirror. This is in Kiel in northern Germany. On this instance, they wanted to put a new fiber optic feed down this road, and they just needed to know whether there was going to be much in the way. So this is just 3 traverses with a 16-channel instrument. So down the road, back up and down again. So very, very quick for data collection and processing. And what we can see is that this roadway is absolutely chock-a-block, absolutely full of utilities. So digging a trench through here to put a new utility through is not going to be an easy task by any stretch of the imagination. But you can see the detail you have in here. You can even see the fall on the utilities as we go up and down through the depths. And of course, it's then very easy to interpret that as to where these utilities lie and where they are in the ground. So just very briefly to finish off, I'm going to look at the MALÅ software options. We have these are, I'm just concentrating on the software that we make ourselves. We have Object Mapper. This comes with the Easy Locator, or works best with the Easy Locator, but can actually be used with the GX, the ProX units as well. And this allows us to look at our profiles where they were collected in relation to each other with a map view, as you can see here. If we've collected it with GPS, then we can put background mapping in as well. It allows us to see more than one radargram at a time. So we can select here, we're looking at 3 adjacent profiles, and we can very quickly go through and put markers in there to denote where there are utilities. With a pretty simple 1 or 2 button export, we can then generate DXFs, and those can be imported in 3 dimensions into CAD or GIS. to show where our pipes and cables sit in the ground. So here we see we've got our blue lines, those are the survey lines, and then we have all of our pick points sat in 3 dimensions beneath the survey profiles. We have a very simple tool called GPS Mapper. We saw that in one of the case studies. This just allows us to plot depth to a feature as a KMZ and import it into Google Earth. So here depth is represented by the color scale, and we can see that just dropped onto an aerial photograph. So really simple piece of software. 3D vision, that's effectively what we had on the CX, that Concrete Explorer, what we see on the instrument itself. This is just an expanded version of that software. Very quickly allows you to do more refined processing on your desktop and to export interpretations from there to give to engineers or whoever might need the results. And then RAD Explorer was one we have. This is very useful for profile mapping, where you're looking at, asphalt mapping, railway lines, geology, because it allows you to very quickly import data, process it, and then define layers. And what's great in here is that we can define different velocities for the different layers by analyzing the shape of hyperbolas in there, and build up a model of the subsurface that can then be exported out to either other software or given as a kind of tabled results or graphic results to engineers. And then my final new for 2020 is MALÅ Vision. This only came out a couple of weeks ago. We did the big launch for this. And this is the way we're heading into the future. This is using the cloud to do all of our data storage and processing. So it's a very, very rapid piece of software to use. You can log on at malåvision.guidelinegeo.com, which is down the bottom there. And this will run on anything because it's based in the browser window. It's, Google Chrome or whatever you prefer to use. You can run it on any device, whether that's a mobile phone, a tablet, a laptop, anything. We can upload the data and start working on it immediately. So it allows us to start doing the processing and interpretation while it uploads the other profiles in the background. And we can very, very quickly make 3D volumes, interpretations, and even export out to a PDF report, all from the same software environment. And what the guys are very proud of is the fact that it's entirely possible to go from having your data on your USB stick to having a PDF document with data images in it and text within 90 seconds. And I don't know if you saw the demo video that has been released. They kind of do it live just to show you that it is entirely possible. But this is the way that we're moving towards, is to have this one software that will kind of encompass all of those things that the other bits of software like GPS Mapper, like Object Mapper, bring them all into one package and make it a package that's easily available and accessible to as many people as possible. And on that front, the good news is that the basic license, the MALÅ Vision community license that allows you to upload 50 megabytes of data but have full functionality, is currently free. So after we finish this, which will be a couple of minutes, do visit malåvision.guidelinegeo.com, register on there. You'll get sent a link with a password, and you can start using the software yourself. We want as many people to start using it as possible and give us feedback. There's a panel in there to send feedback through, like a help page. And so do try it, have a go, see what you can do with it. It's a great bit of software. And every week we add more functionality to it. Okay. I apologize for the my internet connection disappearing halfway through that. I think we lost a lot of people when that happened. But as I say, we'll make sure that we have a single video combined for the whole lot. And we'll put that up online for people to be able to access. So I will just say thank you very much for listening.